Hello, welcome back to electrochemical engineering. Today I'm going to talk about corrosion. Corrosion is inherently an electrochemical phenomenon. Here's a picture of a boat corroding, a wreck that's corroding in the ocean, and as we know, steel, iron rusts. Rust is a form of corrosion, and that's accelerated typically by water and salt. So this wreck has corroded substantially since it crashed on the beach. If you look at a microscopic level, we can understand corrosion, spontaneous corrosion in this case, in the presence of water via the following microscopic mechanisms. Any electrochemical cell needs an anode and a cathode and the flow of electrons and ions. So in this case, we have iron that is getting oxidized. So this is our anode, and the oxidation is creating pits in the iron metal. That's creating iron 2+. That iron 2+ can of course react with oxygen in the environment to oxidize further to iron 3+, which precipitates as an oxyhydroxide out of the water phase. The question is, what's driving the oxidation of this iron metal? Well, the most oxidizing species available is again oxygen, atmospheric oxygen that's dissolved and partitioning into this water phase. And the interesting thing about corrosion is that the site of the cathode and the site of the anode can be different. So in this case, we have a cathode site here on this metal surface, this iron surface, and the iron surface can drive the reduction of oxygen. Remember, O2 is a good oxidant. It's easy to reduce. And when we reduce oxygen, we pull electrons out of the iron. We reduce the oxygen to make hydroxide. Water's involved in that reaction as well. So where do these electrons come from? Well, they can easily come from the iron atoms that are corroding to make iron 2+. So we have a local cathode and a local anode on the same metal. And one thing that's important to recognize is the current here that's flowing is relatively small. So this metal is going to be at some roughly constant electric potential. It's going to be sitting at some roughly constant electrochemical potential, thus, of electrons here. And that potential is determined by, in fact, the rates of the anode oxidation reaction and the rates of the cathode reduction reaction. In this case, the iron is redepositing as solid, and that's the orange rust you see here. The oxyhydroxides typically are hydroxides or oxides if they get dehydrated. But you can also have corrosion just leading to soluble species. Let's take a step back now and talk more fundamentally about corrosion. It's really the unwanted attack of a material by their environment. So anytime an environment is attacking a material via an electrochemical process, we call that corrosion. Often corrosion occurs in aqueous systems, but it doesn't have to. You can have corrosion processes occurring in non-aqueous lithium-ion batteries, for example. We need to understand the conditions under which corrosion occurs, so we need to measure it, the rates, predict it with thermodynamics, and understand how to mitigate it using technology. So there's a large area of science and technology, both in academia and industry, that's focused on understanding and controlling corrosion. The corrosion processes we care about typically occur at the anode, the local anode, where the oxidation is taking place. For example, in the oxidation of iron metal, the corrosion of iron to make rust, you have soluble iron 2+ ions that are formed. And the electrons that used to be on the iron metal, of course, go to reduce oxygen. In this case, it leads to largely insoluble products. For example, salts or an oxide layer, or you can get a mixture of both. As we mentioned in the introductory slide, you need to complete an electrochemical cell for electrochemical corrosion to occur. You typically have a local anode, which is the metal getting oxidized, dissolving, or forming an oxide, and a cathodic reactant, which is often O2, but can also be water. You can reduce water to make hydrogen and corrode some metals if they're very reactive metals. And the key is that the equilibrium potential for the cathodic reaction needs to be higher than that for the metal, and you need electrical contact, and you need some electrolyte conductivity, typically an aqueous phase with a little teeny bit of dissolved ions in it, to allow the passage of ionic current. If you recall from our introductory material, we had this so-called Daniell cell, and the Daniell cell has a zinc anode in this case and a copper cathode. And this is a spontaneous reaction when the zinc dissolves in the copper plates. That's because the copper is more noble than the zinc. So it's spontaneous to take copper from solution, add electrons to it, and to get those electrons from the more reducing metal, the zinc. Fundamentally, this is a type of corrosion reaction. You could imagine that zinc is corroding at the anode, and copper is plating, and then the copper plating is driving the corrosion of zinc to make this whole thing a spontaneous reaction. So if you go back and think about two metals in contact, you can have similar processes occur. For example, an active metal, imagine you had zinc in contact with a more noble metal, like say copper. That zinc could corrode, make zinc 2+. And those electrons could go over here and drive the oxygen reduction reaction. So oxygen going to OH-, right? Oxygen and water going to OH- ORR. In fact, zinc is active enough that it can even reduce water to hydrogen. This is referred to as galvanic corrosion because of the difference in potentials between the two metals in contact. You can also have uniform corrosion, pitting corrosion, crevice corrosion. In these localized corrosion phenomena, crevice or pitting corrosion, the corrosion process is preferred in the pit, for example, due to the local conditions changing there in the pit relative to the external bulk electrolyte. This might be because of a local pH change that facilitates corrosion there. The corrosion we usually care about is occurring on a metal, so it's an anodic reaction. Now, that has to be coupled with a cathodic reaction. And in aqueous systems, as we've mentioned, oxygen reduction, oxygen from air getting reduced, taking up electrons given off by the metals, or water getting reduced, taking up electrons given off by the metal, are the most typical cathodic reactions. Here's the two oxygen reduction reactions in acid and base, and here's the two hydrogen evolution reactions in acid or base. These again are the most common cathode reactions in water. Now, oxygen is only sparingly soluble in aqueous solutions. So what can happen is the reaction can be limited by O2 diffusion to the electrode surface. Remember, in order to dissolve, for example, in order for an iron 2+ to come off, we need to take those electrons and put them somewhere. We need to complete the cell, right? We need to complete the cell. And so we need to have an O2 that can make it to the surface to accept those electrons to drive an overall electrochemical circuit. So therefore, the rate of corrosion, if O2 is the cathode reactant, varies with the thickness of the electrolyte layer, varies with how fast oxygen can get to the surface. You should also recall that the hydrogen evolution reaction depends on pH, and that in acid, its potential is different than in base, and in acid, the kinetics are also much faster than in base. So things tend to corrode much faster in acid than they do in base because it's much easier to reduce protons in acid than it is to reduce water in base. You should also recall that driving the hydrogen evolution reaction, because it consumes protons or generates hydroxides, changes the local pH. So this is important in the crevice example we just showed, whereas if I have a reaction occurring, the local pH, if I'm driving a reaction that consumes protons, so my cathode's over here, the pH over here is going to start increasing as I'm consuming those protons. That will make the corrosion tend to want to continue to occur within the crevice, where it's not as basic as the exterior, where the oxygen reduction or proton reduction reactions are taking place. These are not the only possible cathodic reactions. You can also reduce metal ions in solution. So solutions of oxidizing metal ions like cerium 4+ can be very corrosive. Nitrate, right? Nitrate counterions, nitric acid, they're very corrosive because nitrate is a good electron acceptor. It's very easy to reduce. So metals can easily be oxidized by nitrate. And of course, the acidic conditions facilitate dissolving the metals, so fresh metal is always exposed. So HNO3 Nitric acid is very good at dissolving metals. As I highlighted in the first slide, in corrosion systems, the anode and the cathode are electrically shorted, and they're electrically shorted here by the metal, in this case a bar, that's connecting the local anode and the local cathode. Of course, the thermodynamics of the reaction, which you can calculate in the same way as we learned last term, tells us if a corrosion reaction is favorable and can actually occur spontaneously. Some metals spontaneously corrode under conditions where other metals don't. Favorable corrosion reaction has a negative free energy, of course, which means the cell potential is positive. Remember, U here is cell potential in Fuller and Haarm, when the metal is, of course, acting as the anode. Another thing that's important to remember is that whether a metal will corrode or not, therefore depends on what the oxidant is. Here, oxygen's the oxidant. It's the thing getting reduced at the cathodic site. But if water is the only thing available, say you use up all the oxygen, some metals, water is unable to corrode, whereas they're easily corroded in the presence of oxygen. Let's recall the Pourbaix diagram we learned about last term. The Pourbaix diagram actually tells us a lot about corrosion. We'll come back to this in more detail in class, but let's take a look at it right now. If I have an iron metal and I stick it in acid at pH 0, what the Pourbaix diagram immediately tells me is the potential, E here, for iron 2 plus to iron metal is much less than the potential for H plus to H2. So what does that mean? If I say E cathode minus E anode, I want to find the spontaneous reaction. EH plus minus EH plus, this is acting as the cathode, EH2, minus E anode, E Fe2 plus Fe. This value is greater than 0. So this is a spontaneous when this is the cathode and this is the anode. So iron is spontaneously converted to iron 2 plus by reaction with protons at low pH. The fact that the oxygen couple here, EO2, H2O, is again 1.23 volts higher than the proton hydrogen couple tells us that this number will be even larger. This reaction will be even more spontaneous if you're oxidizing iron with O2 instead of with water or protons. And of course that makes sense. Oxygen is a much better oxidizing agent, so it's going to corrode the iron more easily. Now we can go to other pHs. Let's go look at what happens if you put a piece of iron in base. Well, in base, we have a solid as the product of the oxidation of the iron metal. So the redox potential, the equilibrium potential for the iron oxide couple is right here. And yes, it is negative of the potential for the water hydrogen couple. So in principle, it's spontaneous. Water will spontaneously oxidize iron in base. But first, the distance is small, so the kinetics of those reactions may not be very fast with that little thermodynamic driving force. It's not very spontaneous. And second, the surface of the iron in base will get covered with a solid, Fe3O4. And that Fe3O4 will block additional species from reaching the iron surface and serve to passivate it. So a piece of iron practically will be much more stable in base than it will be in acid to corrosion. Let's define some fundamental terms now. If corrosion is not thermodynamically favorable, it doesn't take place. We call this immunity in the corrosion field. The metal is immune to corrosion based on thermodynamics. But thermodynamics alone can't tell us if corrosion will happen, i.e. it might be thermodynamically favorable, but we need to consider the kinetic rate of the reaction. For example, is it thermodynamically favorable for graphite to corrode in air? What about diamond? Yes, both these are very thermodynamically favorable to corrode to CO2. But it doesn't happen. And it doesn't happen because the kinetics are too slow. rearranging those bonds, breaking the carbon-carbon bonds and making the carbon-oxygen bonds, is a very difficult, kinetically slow process where you have to go over a large activation barrier. Now, some metals are thermodynamically favored to corrode, but they're stable due to a passive layer. A passive layer is typically a dense oxide surface film that impedes further corrosion. One example is aluminum. Aluminum forms Al2O3 on the surface, and if you take a piece of aluminum metal and you put it in an electrolyte and you apply a positive voltage to that metal, you might have a cathode over here, you can intentionally grow a thick, dense film of aluminum oxide, and we call that anodized aluminum. You've had anodized aluminum all over the place. Your laptop, your bike, things like that are often have anodized aluminum pieces. And you do that so you get a nice, thick, dense layer of aluminum oxide that prevents any other corrosion from happening under natural conditions in exposure to air and rain and water from rain. And that allows you to maintain a nice finish on aluminum metal. pH and applied potential are, of course, variables that determine the stability of electrode surfaces, and this is where Courbet diagrams come in, and you guys have a deep understanding of Courbet diagrams from the previous fundamentals class. Let's review Courbet diagrams quickly, however. Courbet diagrams are defined for a total concentration of soluble species, here 1 micromolar. So in this region of the Courbet diagram, there'd be 1 micromolar of soluble nickel 2+. If a potential is applied to a piece of nickel, and that potential is very negative, say down here, -1 volts versus SAG, that nickel will be in a region of immunity. Call that immunity region. The electrode is poised at a potential where thermodynamically it can't corrode. Now the surface of the nickel, if you poise it at this very negative potential, can drive other reactions, for example, reduction of oxygen or reduction of protons to H2, but fundamentally, the corrosion reaction is prevented by the applied potential. Passivation of nickel is expected in regions where a solid nickel-containing species is stable. Examples are nickel hydroxide, nickel oxide. This region here is the passivation regime. It's about pH 9, pH 12. If you go much more basic, there are small amounts of soluble nickelate species, and then you have another corrosion regime. Notice that the passivation regime extends over a large pH range if you get to very high positive potentials. When you start accessing nickel 4+, and here nickel 4 oxide, is much less soluble than nickel 3 or nickel 2, and the reason is because nickel 4, you form very strong ionic bonds with oxygen, and those strong ionic bonds, because of the high charge on that cation, prevent the thing from dissolving. So that's a very common thing with metals, is they're more soluble in 2+, 3+ state than they are in higher oxidation states. We can also imagine measuring a current voltage response for a passivating film. Here's an example from Fuller and Harb. Here's an IV curve for a passivating metal. So you could imagine this is a piece of aluminum, for example, driving an oxidation reaction. You first start to see a large increase in current, and that's due to the oxidation of the surface here, say Al2O3. But as that surface oxide forms, it eventually starts to block the transfer of any ions into the aluminum, any hydroxides or oxide ions, to make any more Al2O3. So the oxidation reaction stops and the current drops to be very low. As you keep increasing the current, we call this the passive region, where you form this insoluble metal oxide. You keep increasing the current, at some point you get what's called breakdown. And then at this condition, the electronic charge is actually able to tunnel through the oxide layer. We call that breakdown of the oxide, or the trans-passive region. So if you know something about dielectrics and gate dielectrics, those things break down when you have a large voltage across them. And that's due to various mechanisms, including tunneling and hopping and defect-related transport of electronic charge through the oxide. It's interesting to talk about the current voltage behavior we've just discussed in the context of aluminum corrosion in non-aqueous battery and supercapacitor electrolytes. So aluminum is one of the electrodes used in a lithium-ion battery. So what you see, an electrolyte that's pure lithium TFSI in a mixture of ethylene and dimethyl carbonates, common electrolyte for lithium-ion batteries, you see at about 0.5 volts here versus this reference and 3.5 volts positive of the lithium plus electrode. You see a strong anodic current that's associated with corrosion of the aluminum, dissolution and corrosion of the aluminum, which is exactly what you don't want to happen. But if you make an electrolyte with lithium PF6 1 molar, that corrosion is substantially suppressed. And in fact, you only need to add very small amounts of the PF6 salt to suppress that corrosion. So there's a role here. These are called additives. This lithium PF6 is another salt, but the properties of lithium TFSI are better for other reasons. So we just add a small amount of that in this case to prevent the corrosion of the current. And really at the high potentials where you have a lithium-ion battery cathode, the high energy cathodes, they're typically at 4 to even 5 volts versus lithium plus. You get a lot of complex chemistry that's possible. We'll be discussing SEI layers again coming up in future lectures, but this nice paper, or this diagram, shows some of the phenomena that can go on. So ethylene carbonate, right, can get oxidized at those high potentials. That can lead to pitting corrosion, for example, generating free protons, acid, making HF, etching aluminum fluoride. Those can affect the SEI. The chemistry is very, very complicated. So one of the most common ways you characterize corrosion, the rates of corrosion, is with what's called an Evans diagram. An Evans diagram incorporates Tafel plots for the anode and cathode onto the same plot versus a common reference. And you might ask yourself, well, how would you get this data? Well, you can go and measure, for example, a Tafel plot for iron dissolution on an iron electrode with a well-defined reference, well-defined mass transport, etc. You can go and measure a Tafel plot for hydrogen evolution on the same metal with an electrode and an electrochemical cell with a well-defined reference. And what we can do is we can plot these on the same Tafel plot here. And as you notice, for the hydrogen evolution reaction, as the potential goes more negative, down, the current goes up. For the iron dissolution reaction, as the potential goes more positive, the current goes up. Of course, if we have a cell where you have iron dissolving and hydrogen getting evolved, where electrons are coming from the iron, reacting with the protons and making hydrogen, the current associated with iron oxidation must be equal to the current associated with proton reduction. So we can go on this plot here, and we can see where those two Tafel plots intersect. You can see they intersect at the corrosion current for the system and the corrosion potential. So what the corrosion potential tells you is it tells you the potential, we call that a mixed potential because the potential this metal is sitting at is controlled by the kinetics of two reactions. It's controlled by the oxidation reaction and the cathodic reaction. And for example, if I improve the kinetics of hydrogen evolution, if I made this a much better hydrogen evolution catalyst, the curves would cross over here and the mixed potential would be different and the corrosion current would go up. So it really depends on the kinetics of both reactions where these two Tafel plots intersect. So what's interesting here is the surface is simultaneously doing both oxidation and reduction. I say here, how? Well, the answer is pretty straightforward. The equilibrium potential for iron is down here. Notice the equilibrium potential is where the current goes to 0, so the current's tending towards 0 here. The equilibrium potential for the hydrogen evolution reaction is going to be somewhere up here, right, versus SHE. And so simply put, the corrosion potential where this piece of metal ends up is somewhere in between the equilibrium potential for the anode and the equilibrium potential for the cathode. Somewhere in between. If the cathode has really, really fast kinetics, it will move towards the cathode. This curve would move over. If the anode had faster kinetics, the equilibrium potential would move towards the anode. Or if I slowed the kinetics of hydrogen evolution down, then I intercept down here at a smaller potential and I decrease the corrosion rate. So to emphasize the potential of an electrode, no wires on this electrode, potential of a metal sitting in the solution corroding naturally moves to the so-called corrosion potential in a uniform corroding surface. This is because the anodic current has to equal the cathodic current. And again, to emphasize, you can tell from the plot where the equilibrium potential is for a given reaction. Here's the iron dissolution reaction by just following this curve back to zero current. So again, the corrosion potential is the potential at the intersection point of the two curves. The corrosion rate is the current density at the intersection point of the two curves. It's the rate. It tells you the rate at which the metal will dissolve. The overpotential for either the cathodic or anodic reaction is given by the difference between the equilibrium potential and the corrosion potential. So this is eta anode and eta cathode. The equilibrium potential somewhere up here for hydrogen. Remember that V core and I core are concentration and temperature dependent. If I increase the temperature, corrosion rate will probably go up because the kinetics of all these reactions go up, so I need less overpotential to drive the corrosion current at the anode and cathode simultaneously. So let's go through this mathematically. If the exchange current densities and the equilibrium potentials are known for an anodic and a cathodic reaction under known conditions, you can actually solve for V core and I core analytically. And this is something you should be able to do, for example, for the exam. Let's get some nomenclature out of the way. We're going to call little a and little c the anodic reaction and the cathodic reaction. So you'll see these subscripts here. Do not be confused about how they are responding in the Butler-Volmer equation to the anodic and cathodic branches of the Butler-Volmer equation. These are not two branches of the same chemical reaction, the same kinetic expression. They are referring to different reactions, the anode reaction and the cathode reaction. The anode reaction, remember, is going to be the dissolution of metal, the oxidation of metal. The cathode reaction, for example, will be the reduction of O2. And B is going to be the Tafel slope, which primarily is a experimentally measured parameter, though you can write it in terms of the transfer coefficient alpha. So the Tafel expression, this is ignoring the reverse reaction, is just I naught times the exponent of the anodic transfer coefficient times F over RT times the overpotential, in this case for the anodic reaction. Now we can solve for V core by simply setting the total current equal to 0. So we can set the sum of the Tafel current in the anodic reaction plus the Tafel current in the cathodic reaction to 0 and just rearrange to calculate the overpotential where that works for both reactions. Remember, the overpotential can be written as the difference between V core and the equilibrium potential for the given reaction. I'll leave this as an exercise for you during class. We'll go through this. The corrosion current can also be calculated as soon as you know the corrosion potential, and that's given here in this equation 16.6b. So that's all I'd like to discuss today, and I'm looking forward to going through some of this with you in class soon.